Finding your way in, please find a seat while we get set up here. I want to welcome everyone here this evening to this plenary lecture by Professor Susumu Kitagawa. It is my honor to be here. This is not my field, but I'm looking forward to learning a lot this evening. Professor Kitagawa received his undergraduate and PhD degrees from Kyoto University, working in the area of hydrocarbon chemistry. After appointments, first at Kinki University, and then a year in Texas, later with Al Cotton at Texas A&M, and later moving to Tokyo Metropolitan University, Professor Kitagawa returned to Kyoto University, where he later became director of the Institute for Integrated Cell Material Sciences. As a leading scientist in the field of porous coordination polymers, which are now finding new uses in many areas, including gas storage, chemical sensing, and drug delivery. This is an amazingly new and promising field in material science. In recognition of his research, Professor Kitagawa serves on numerous editorial boards, has received many awards and other forms of distinction, including the Chemical Society of Japan Award, a Fellow of the UK Royal Society of Chemistry, the 2016 Japan Academy Prize, and was the 2016 Fred Bosselow Medal winner for outstanding research in inorganic chemistry. Many other awards as well. Please join me in welcoming him to the podium for his plenary lecture.
Very kind introduction. So I'd like to thank the organizers, in particular in the Professor Dejiraju, for inviting me for the fantastic and the superb conference. I'm very honored to give this lecture. So, before talking my chemistry, I'd like to inform you that most of the audience knows in the field of materials, the great Professor Gerard Ferret passed away in the last week. So it's a great loss in our science. But he contributed very much his achievement in the material science, of course, in particular in the inorganic materials and also the metal-organic frameworks. And he produced a lot of the very fantastic metal-organic frameworks. So I'd like to dedicate my talk to great Professor Gerard Ferret. Okay? So let me start with this slide. With the Industrial Revolution, human created a huge amount, the technology that consumes a huge amount of energy. So, initially, people used coal. People used coal. But in the 20th century, as you know, of course, this is the liquid, and the petroleum, of course. But what about 21st century? That is the gas. For instance, in the natural gas, most of the people knows this underground resources will disappear. So we have to seek new resources. So the important thing is the ubiquitous materials. So that's biomass or CO2 or air. So gas are very important. So the technologies are changing, and from the gas substance, the solid to liquid to the gas. That's very important. So please look at this one. And you see, in this axis is the year and the population. We are standing right now. So this is the developing country, increase more and more. And this is a very bad message from the United Nations. In the 2050, we have the 9.8 billion people. In 2,100 year, this case in the 11.2 billion. So huge amount of people will live on our planet. So what we shall do for the future? That's a very important issue. So several years ago, I remind our scientists, gas are very important. We have to develop more and more the science and technology for the gas substances. So these are very simple gas substances. Most of the people knows everything. So these gases are involved in the environment, of course, and also the natural resources, energy, of course, even in the case of life. So we have to develop more and more this technology for gas substances. So this is the UN set up the Sustainable Development Goal, SDGs, to the 2030. So this goal for our chemistry or our science is very important. For instance, in the food and health, water, energy, industrial innovation, sustainability, climate, life below water, life on land, all things are strongly correlated to the gas substances. But still we have the difficulty to handle these gases. For instance, they diffuse very fast, and usually a certain kind of gases are very unstable. And also we cannot see these gases. So it's very, very difficult. In order to handle these gases, we have to develop more and more new substances that are porous materials. So today I'm going to talk about porous materials, new porous materials. By using this, we can control very easily from the separation, storage, conversion, and so on and so forth. That's very important. But we have to think about this, how we can synthesize this type of materials. Of course, we have conventional materials, but we have to synthesize more and more precisely. So we have to design the new type of materials for the special target. So this is the idea. Just think about it. Construct like this. But very beautiful, but it takes a long, long time. But it's okay. We have the very strong tool. That is the coordination bond. This is very important. By using this bond, we can make this type of the framework, metal complexes like this. We can construct three-dimensional structure. That's the point. So you have organic molecules and metal ions in solution. In a minute, you can get this type of beautiful, regular structure. So the structure is like this. This is nanoscale, you see, and this is the metal part and the organic part. So we can construct this one. So this structure expands more and more to the bulk scale. This is very important. And for instance, you have 1 micron crystal, very small, tiny. It's very difficult to see, but we can determine the crystal structure. And you see, like this. So this size around 1 nanometer, but on this side, 1 micron. That means 1,000 and 1,000. Totally, you have 1 million channels in this way. So the channel is like this. And the molecules, for instance, CO2 are incorporated like this. The interaction between the CO2 and the surface is very strong because the distance is very short. So what we call these type of compounds, they are called porous coordination polymers, PCPs, or metal organic frameworks, MOFs. But by designing this metal site and also the organic molecules, you can construct like this. So very easy. So I have to say just the definition of the metal organic framework or porous coordination polymers. So coordination polymer is like this. Just coordination compounds having the extended structure from the 1 to 3 dimensional structure. And what of the coordination network? That is the network, and it's easy to imagine about the 2 and 3 dimensional structure. But even in the 1 dimensional case, in the solid, there is a certain interaction between the chains. So we have the network structure in the solid. So among solid network structure, and if they have potential voids, we call metal organic framework or porous coordination polymer. That's the definition. IUPAC recommended this definition, not decided yet. Okay, so and almost 20 years ago, I classified these type of compounds, and just like this, first generation compounds, second, third generation compound. So just I want to introduce what is first, second, and third generation compounds. So, and this is just history. In the DT metal organic framework, DT means the metal ion having 10 electrons in the d orbitals. So this is old structure, but the Professor Saito, he was a very famous person in Japan, a crystallographer, and they determined the crystal structure of copper 1 and the nitride metal complexes. Very beautiful network structure. And 30 years later, Richard Robson also synthesizing this type of the diamondoid structure, the copper 1 and the nitride type of compound. And also the silver compound is synthesized like this. But we have drawbacks because the structure is very beautiful, having the porous structures, but once you remove the gas molecules, the structure collapses. We cannot use this type of framework. Why? So just look at the energetics of the metal ligand binding, and this type of compound have just 100 kJ per mole, very weak. So that's the reason why the structure is very collapsing. Just this is the post-it. Easy to make, easy to break. So we have synthesizing the new type of system using the cobalt-2 and bipyridine, and synthesizing this type of the framework. By using this, after removing gas molecule, the structure is maintained. So we can carry out this type of gas absorption. And also the Omayagi and carried out this type of gas absorption using the zinc type of compounds. So why this structure is stable? Metal ligand binding showed these energies are larger than the 200 kJ per mole. In the case of copper-2, the carboxylate, in that case, the binding energy is nearly 400 kJ per mole, very strong. That's the point. So we have the second generation compound that shows the structure is maintained even after you gas molecules. So we have a robust structure in this way, okay? So what is good for small pores? So the second generation compound have 3 keywords, 3 attributes. First one, topology, what kind of network we have, then surface area, and also the porosity. That's very, very important topics in that almost 15 years ago. All the researchers are focusing on these the attributes. So let me tell you why this type of porous materials, porous pore is very important. For instance, you have this kind of this type of the cube structure, and so the inner surface area is just 4 square centimeter. But if you have 1 micron channels, in that case, you have 400 square centimeter. And in the case of 0.8 times 0.8 square nanometer cross section, and because the methane is accommodated in this way, so you have 2,200 square meter, very, very big one, like this. Maybe several people knows. In the one space, we can accommodate many people. But anyway, and the zeolite, you have around the 500, and in the case of active carbon, 2,500. But in the case of our porous compound, the very huge square surface area, like this. What the synthetic method? Just I showed you, and this is the metal ion solution, and this is the organic ligand solution. This is real time. You can get it. Even mathematicians can synthesize this one, like this. This is exactly the structure in that way. So another method is a solid state synthesis. We don't need to have a solvent. Just grind these materials, and in the 10 minutes, we can get very beautiful crystalline materials. So thanks to this, important things, and this is the published papers or reports, and yearly the amount, the published number of papers are around 7,000. Many people published the papers or patents regarding this type of materials. So today is the time is limited. Just I'll show you several functionality. And the first one is storage and methane storage, CO2 storage. This materials has high power, high capacity for this kind of storage. But just I want to show how we can store the dangerous materials, very dangerous one. That is acetylene, for instance. It's very dangerous. This is just after the explosion of acetylene cylinder, in that case. If you apply the pressure to the 2 bar under the room temperature, abrupt explosion occurs. So we synthesize this type of materials, and using the copper and the organic ligand, they give the layer. Layers are linked in this way to give a pillar layer structure. So we accommodate acetylene because in this case, we designed the double hydrogen bonding system. Okay, acetylene has hydrogen and the oxygen in this case. So we can accommodate acetylene. The density is the 200 times larger than the usual the complexity limit. So very stable. So by using this, so you can incorporate like this. So, and there are many porous materials to date, and the zeolites and the MOFs and also COFs, PIMs, and just the molecular compounds. So these type of compounds contain the organic molecules, but in this compound contains the metal ions. Okay, we can draw this line, and also, and in this case, we can draw this line. So our compounds are very special because contains metal ions and also organic molecules. So that's the point. So this is very famous toy. You can change the structure very easily, but only the angle changes. So so we call this type of new materials is a 3rd generation compound. If you remove the gas molecule, the structure converted one form to other. So in this case, in the 3rd generation compounds, there are 3 attributes. First one is the flexibility, the second, collectivity, and third, diversity. Diversity, as you know, we use the organic molecules and metal ions, also the spin, the electrons, and so on and so forth. But in the case of flexibility, that's very interesting. So, in the conventional materials like this, gas molecules is accommodated in like this. If the size are very small, this cannot accommodate it. This is separation. But our compound like this, and the gas molecule incorporated, but the structure changes in a way well suited to the gas molecules. That's very important. So then the next one is the collectivity. This is also very important. For instance, in the just a cage, one molecule, the response is like this. But if these pores are interaction with the like this, and we have this type of the sigmoidal curves. This is a lesson from nature. You have the myoglobin in the muscle, and also hemoglobin like this, and the blood. So in the myoglobin show this option for the oxygen, but the hemoglobin like this because of collectivity. That's very important. So we have the idea how to synthesize, how to construct this type of materials. If you have the layer type compound, this has a sort of the mutual dislocation. And the second one is the hinge type structure. And even in the case of rigid one, interpenetration is very important like this. And the interdigitation also. So this is the new properties in case of porous materials. So from the static to the global dynamics, in addition to global dynamics, we still have the local dynamics. That's very important. So let's see the flexible porous compounds. For instance, we have synthesizing this type of materials, and by using this, we can recognize the supercritical gas. For instance, in the methane, O2, nitrogen, CO2 at room temperature. So the interaction between these gases is very small, but we can recognize, we can distinguish these gases. So this is the reality, and you have the metal copper, and this ligand gives the layer, and also this has the just kind of pillar. The motion is like this. So we can accommodate the gas. So in a certain pressure, the gate abruptly opened, and reduce the pressure, the gate closed like this. So the Gerard Ferret also the very interesting expandable porous materials. That is very fantastic. So let's see the energetics of this and the type of systems in the open home and the closed home. So they cooled out and they calculated thermodynamically the open home and the closed home. In the just the difference, energy difference is 4 to 5 kilojoules per mole, very small, because this is the collective phenomena. Cooperativity is very important in these materials. So the IUPAC isotherm patterns, there are many patterns in the 1 to 6, but our sorption style is completely different. It's a kind of discovery. Why this is very important? For instance, usual sorption like this, and at this point, you can get the full loading, but if you want to get the loading in this case, and for instance, and very tiny amount you can take, but if you have this type of sigmoidal curve, you can get all. So this is very important. So we are chemists, we can modify this kind of sorption profile like this. That's very important. But of course, we have advantage to the recognition and selectivity because of soft materials. But the problem is disadvantage to pelletization and durability. So many times it's possible. So this is one example we have synthesized. This is the interpenetrated systems, okay? And we carried out, this is pelletized, okay? Then we carried out sorption, desorption, sorption, desorption, this experiment. We carried out this experiment in the 600,000 times. So this is capacity. If the 100%, the capacity is maintained. So after 600,000 times, still this capacity is maintained. So the pellet is like this, before, after, so it maintained. So this is very fantastic, and capacity and also durability in this case. So the separation is very important, of course, and this is the recent commentary in the Nature. This shows the 7 chemical separations to change the world. That's very important, and in particular, in the processes involved such as distillation accounts for 10 to 15% of the world's energy consumption. So it's a huge energy for the separation. So in this paper, just show the 7 separations, but we have many cases for the separation. But more or less, these cases show a sort of the gas phase separation. So please look at this plot, and this shows the molecular size. This is building boiling point, indicating a kind of the measure for the ease of separation. And for instance, in the CO2 and methane, the distance is very far. That means the easy separation. The similar things in the CO2 and nitrogen or oxygen. But okay, so this is just the review paper, listing the CO2 separation using MOFs and PCPs. There are so many compounds so far synthesized. But if you look at, for instance, and xenon and the ethylene, CO2 and acetylene, and argon, O2, and CO nitrogen, the distance is very close. That means it's very difficult to separate this mixture. So let me tell you about the CO2. CO is very important, but they produce a lot from the, for instance, steel company and so on and so forth. So for instance, this is the activated carbon and the single sorption, but we can see this is pressure and the adsorbed amount, and you see almost a similar sorption profile. That means it's difficult, impossible to use to separate this gas mixture using the activated carbons. And this is the famous MOF5 and ZIF, and also the HKUST1, and this is just compound. They are representative of the MOF compounds, but very difficult to separate. So our colleagues synthesizing the new type of materials using copper and isophthalic acid like this, like copper units linked to the extended structure like this. This is basically in what we call the Kagome lattice. So by using this, we can see the big difference between the CO sorption and nitrogen. Good news. So what happens in this case? So as synthesized compound show like this, and this is the Kagome lattice. There is a big cross-section and a small cross-section, but after treatment, and this shows a sort of the different type of structure, and the small one shows just isolated pores, completely different. But what's happening? So we see just the diffraction method and diffraction patterns about this in particular in the low angle part, and this is the sorption profile, low pressure, and this adsorbed amount, A, B, C, D. Nothing happens in this case. But in the case of CO, and from the A, B, C, nothing happens. But after C, the new peak appears, indicating the structure converted one form to the others by CO sorption. That's a big difference. So we determine the crystal structure, and the small channels show the just open gate like this. What's happening? In this case, in the CO coordinate to the copper 2+. Coordination is very important in this case. But I have to remind you, this is kappa 2. Usually kappa 1 has a strong interaction with CO, but not kappa 2 because the energy is very small, 20 kJ per mole. So at the beginning of my talk, I showed you, in order to prepare the very robust framework, we have to have the energy larger than 200 kJ per mole. But for the recognition, or for the capture of the gas molecules, the energy is only 20 kJ per mole. That's enough. This is very important. So for the capture with low energy, that means we can release with low energy. That's very important. So to make the long story short, just I want to show what's happening in this case. In a small channels, the 3 CO coordinate to 3 copper atoms. So this induces the gate opening in the neighbor. So this is a sort of the self-accelerating absorption, the reminiscent of the hemoglobin. Like this. Okay. So we want to know what's happening in this case. Of course, we can determine the initial state and the final state. But we want to know the intermediate state. That's very important. So it's very difficult to see what's happening by usual X-ray diffraction method. So we are thinking about this kind of snapshot. And this is very important. So in Japan, we are very happy to have the Sakura FEL system. And the audience most knows, just skip this one. And we're setting up the observing system. And we observe what's happening in this case. This is the final state, and this is initial state. The diffractions are different because the different phase. So we observe this one. So we succeeded in just getting the transient. Okay, this is the initial state, and this is desorption, absorption. In between, we have the transient state. So like this. So this state is completely anisotropic. But still, we have the several data we have to have. So under investigation. But this is a good sign by using the very fantastic facilities. So this is I want to show you the future. But anyway, we synthesizing various type of the ligand systems. We are chemists. We synthesizing framework by using the different type of ligand systems. And we try to have the very good system. But for the application, in particular in the industrialization, we have to have a scale up. In the case of synthesis, this is just a synthesis. Very easy, okay? We have developed. So thanks to this, we can scale up right now. And also, we can get the tableting like this, very fast. So this is the very robust and the tablet. But anyway, and I'm talking about the third generation compounds, but many people ask me, what is the fourth generation compounds? So I think a little bit complicated. So these keywords are very important. First one in the hierarchy, hybrid, and 2H, anisotropy, asymmetry, defect, disorder. HAD is very important. And by these keywords, for instance, just today I will show you the melting problems, the PCP MOF science, and also the downsizing is also very important, and hybridization. So melting. So before I'm talking about this one, we are focusing on not only gas substances, but also the small cations and anions. That's very important. For instance, in the fuel cell, the audience knows we have the materials performing at high temperature and or low temperature, but we don't have the system working at the intermediate temperature. The intermediate temperature is very important. This is the famous fuel cell car that contains the naphthalene. So it works under 80 degrees Celsius. So in order to keep this system, we have to have a very big, huge cooling system. And also the other point is the high cost. We need to have the large amount of catalyst and also the strong demand for the fuel system. So this is the temperature and the proton conductivity. Or in the case of naphthalene, after 100 degrees Celsius, the conductivity decreases. Of course, the water molecules are removed after 100 degrees Celsius. But our compound shows still the conductivity increases. So usually the proton conducted using this type of the water. But if we use this type of the imidazole, and for instance, we synthesize this type of materials, just incorporating the imidazole into the channels. Also, the Professor Shimizu and the University of Calgary is synthesizing this type of material using triazole. The similar thing happens. And let me show you what's happening in this case. So by sublimation method, we can introduce the imidazole into the channels. So by heating, the imidazole rotate faster and faster. That means we can transfer proton from the one imidazole to the others. Okay, that's very important. But this is very difficult task because we have to design very, very clearly for the channel size and the shape like this. Okay, it's very, very difficult task. So we change this system to the other one. That is phosphate. And this is solid state synthesis. Just put the component in the grind in the 10 minutes, you can get very beautiful structure. And this is just a connection of phosphate and also zinc ion, basically one-dimensional channel. And on this channel, the phosphate is attached like this. And this one-dimensional channel, the running from the back to the front. And in between, there is the imidazole cations. Okay? So we determine the crystal structure at minus 50 degrees Celsius. So we exactly determine the position of the atoms of the imidazole cations. But in the case of 80 degrees Celsius, dynamic disorder happens. It's very difficult to see. That means the imidazole rotates very fast. Okay? Like this. Like this. So the conductivity increases around the increase of temperature. This is very good news. And so the prevailing the opinion was that the MOF decomposes when heated to the critical temperature because of the instability of organic molecules, like this. So MOF and PCPs are the crystalline materials, so after the high temperature, the decomposition occurs. But if we have the liquid phase and also glass phase, it's very good science for the future, okay? Also technology. So we are seeking this type of compound, okay? And we heated these systems. So what's happening? And as I showed you, this one, the imidazole rim, they rotate at high temperature. So this is DSC by heating. Okay, the adsorption heat occurs like this. So this means the abrupt rotations of the imidazole rim, cations. But my student is so smart, but at the beginning, I thought that he was so stupid. But he's very smart because he heated again, and he observed a very, very big absorption of heat, okay? So he observed the liquid state, no decomposition, liquid state. So that means from crystal to liquid state, liquid to the glassy state, and converted to the, crystal like this. So this is NMR, and at the liquid state, of course, in the phosphate show the very sharp line because isotropic, like this. And we can determine the structure about the glassy state. It's amorphous state, and using the RDF and PDF. And so this is the pair distribution functions. That means still we have the correlations, but the big issue is like this. And around 6 angstrom, the structure is maintained, but we cannot have the long range order, of course. This is the amorphous state. So, but the important thing is we have the melting phase, and then convert it to the glassy state. So we put this liquid on the substrate, and we observe this, like this. So this is the powder. This is the thin film on the substrate. It's very beautiful. The alignment occurs in this case. So, and just I told you the global dynamics is very important. Flexibility, the softness, but local dynamics is very, very important. For instance, okay, we switch the system and using the triazole and synthesizing new type of compound that is layer type compound. Zinc is connected by this triazole. They give the layer systems, and each zinc has the phosphate like this, okay? So phosphate can rotate. So the local dynamics is very important. So MOF and PCP have very, very interesting properties because of local dynamics, okay? So, and of course, we can get the melting phase and also the glassy state phase. So we can, this is the glassy state and also the crystalline state. And we can make thin film. That's very important for the cell, field cell. And so, and the conductivity is increases in the case of, in particular, in the glassy state. And so, please look at this is the just a field cell we constructed using this one. And so, and we introduce the hydrogen in the field cell. Temperature is over 100 degrees Celsius. So what's happening? This rotate. That means it works. So the thin film, our materials. Why we can synthesize, we can prepare this kind of materials? Because we have melting phase. So this is one example about the melting. And the other thing that does downsizing, and this is also very, very important in our materials. And just to show the one example, and this is the interpenetrated framework I showed you before. And we modified this system because we used the longer ligand, okay, longer ligand. So because of long ligand in this case, and as a synthesized compound show this type of very beautiful, the grid type structure, but once remove the gas molecule, the structure deformed like this. And today I don't tell you about the how we can control crystal size, but very easily we can control the crystal size. We call this method and the coordination modulation method, completely chemical method. So this is crystal. The size is from the 45, 60, 110, and 160, 300, 500 nanometer, okay? We synthesize different types, size of the crystals. So we observed what happening, just full loading and after removing gas molecules, what happening in this case. So this is just the results. And in the bulk phase, large crystal shows once we remove the gas molecule, the structure collapses like this. This is closed form. But in a certain size of crystals, for instance, 60 nanometer, and you see this open form is maintained even without the gas molecule. And then by heating, by giving a stimulus, the structure converted to the closed form. So this is a sort of the shape memory effect, completely different from the bulk state. So this is also discovery. And this is just a summary. And if you're synthesizing the certain compounds, but you have a chance to change the crystal size for the discovery of new properties. And this case, and from bulk scale, this is the closed form and open form like this. But in intermediate case, we can observe the shape memory. The structure is still maintained. And in a nanoscale, for instance, cage compound, and the structure, of course, is maintained. But this is just intermediate properties. So the downsizing is very important. So from bulk scale to the intermediate phase, mesoscale phase, and also the nanoscale phase. So we have many chances to see the new properties. So, and the fourth generation compounds are a little bit complicated, but I would say thanks to the crystallography, we can get very beautiful structure, and also we have the methodology and the design the new type of compounds at will. And then we are moving to the sort of the complicated systems that have the defects, disorder, and also the anisotropy, and so on and so forth. So this is my dream, and one day I want to synthesize this type of the aggregate, but this has a kind of the anisotropic functionality, and from the separation to storage, conversion, and also the transport. But right now we have just a type of the sandwich type or core shell, and this soon after, and the young people in particular, and have a challenge to synthesize this type of new system. Okay? So just a story today I talk about, and I have to thank the many collaborators, students, and they contributed very much. The curiosity, scientific curiosity is very important. I think after that, we have a chance to have a industrialization. But the porous materials, at the beginning I showed you, the porous materials are very important for the science and technology for gas substances, in particular ubiquitous gas, and that's very important. So I have to thank also the funding agencies, and also the Spring 8 and Justly. Thank you for your kind attention.
Take questions.
Yeah, yes.
Well, thank you very much for that informative seminar, lecture. Obviously, a lot of work has been done, but there's a lot of work to be done yet in the future, so take advantage of this. There's time for questions. If you bring just take advantage of one of the microphones and come up and ask questions.
Fluorinated compounds. I know fluorinated compounds like to take oxygen, for example.
I'm sorry, would you repeat the question?
Hold on.
Oh, okay.
I have to find the right distance. Now I know that perfluorinated compounds do absorb oxygen, for example. So I'm wondering in MOF, if you have a lot of fluorine there, what's happening? Is there some literature about that?
Yes, it's very, very interesting and the task. Yeah, we are doing. But the big issue is the cost issue for the application. Yeah. But as a science, it's very, very important. Yeah, we are doing so.
Hi, Professor. It's really amazing and excellent presentation. So I have a small doubt here. Is there any real applications which have crystalline shape memory materials?
And our compounds, yeah, just separation right now. And just separation for the, in particular, the CO and 2 mixture. But the industry produce a lot of CO. The one CO into the air, it's a mixture of CO and nitrogen. It's very low quality gas. So if we carry out the separation very easy, we can reuse of CO. That's very important. And the other thing in the olefin, olefin and the alkan separation. Right now.
In that science paper, you did only pure isotherms, right? CO and nitrogen.
Would you repeat that and speak up, please?
In the science paper, only CO and nitrogen pure isotherms are there. How about the mixture of gases? What if we pass mixture of gases, CO and nitrogen? So how it appears isotherm? Is that, do you have any breakthrough data on that compound?
Yeah, of course. Of course. Today, I'll talk about the science, the just chemistry, but we have already, in the 4 years, we are working on the proof of concept, using the 2 towers for the separations. We have a lot of the pellets, just I showed you, pellets.
Yeah.
They put in the columns, in the separation, we carried out.
Yeah,
the breakthrough curve, of course.
Yeah, usually for flexible MOFs, once gate opens, in flexible MOFs, once gate opens, if CO is going, the nitrogen also easily enters.
No.
Yeah.
That's the fantastic mechanism. Okay, only CO can open the gate.
Okay.
See, 3 CO come in the just a pore. The pore is not so large. So the 3 CO, that means no space to go through.
Okay.
Nitrogen cannot go through in the space.
Yeah.
So only CO can go through to the channel.
Yeah, that is the first paper which is reported for in situ CO gas option. There is no other papers even before now also. Yeah. So thank you very much. Yeah.
Well, if there are no further questions, let's thank Professor Kitagawa again for an excellent lecture. Banerjee from the local committee, up to the podium.
On behalf of the local organizing committee, it's my pleasure and real honor to present a small token of appreciation to the plenary speaker, Professor Kitagawa.
Thank you.
Also, on behalf of the local organizing committee, it's a real honor to present a small token of appreciation to the chair of this plenary talk, Professor Marvin Hacker. Thank you very much.